All right, good morning, everybody. Thanks for joining us for Blackhat relatively early hour and for making the long journey down unmarked hallways and having the dedication to actually find the room. So my name is Brad Hill. I'm a principal consultant with ISEC Partners.
My name is Scott Stender. I'm a partner at ISEC Partners.
My name is Rachel Engel. I'm a security analyst at ISEC Partners.
And we all work in their application security consulting practice, and the three of us are based out of Seattle. So we're here this morning to talk about attacking Kerberos deployments. Kerberos is one of the oldest security protocols that's still in wide use. And as for any protocol that is of that age and that level of complexity in deployment, there are lots of caveats, warnings, configurations, and notes in RFCs and policy statements and operating systems for configuring it. And these tend to be kind of cryptic and hard to understand, so much so that just about every deployment we've ever looked at has at least some set of services that are not taking advantage of the full set of security properties available of Kerberos or are configured in ways that are just wildly insecure, unfortunately. So we're here to, we read the RFCs so you don't have to, and read the policies so you don't have to, and we're going to explain to you what do those warnings actually mean in terms of practical attacks, and what can you do as developers and as administrators of these systems to make your lives more secure when you're using Kerberos. So we're going to start today on our agenda with a quick overview of the protocol. So those of you who don't live in the jargon every day like us will have some idea what we're talking about when it starts to fly. We're going to talk about the initial authentication steps of Kerberos and some attacks against E-type negotiation. We're going to go into public key Kerberos as it supports smart card login and look at an attack there that is active against just about every single Active Directory system deployed in the field today that allows user-to-user elevation of privilege. And owning one box, eventually elevating to owning an entire enterprise. And then we're going to look at the establishment of sessions to applications with Kerberos and how those might be hijacked and what are some of the precautions that we can take to protect against replays and ensure that we're talking to the services we really think we are. So, a very brief introduction to Kerberos. Kerberos is a trusted third-party symmetric key exchange protocol based on the Needham-Schrader protocol from 1978 and then formalized over several versions into the current form of Kerberos 5 today. But the basics are still the same. You have a trusted third party, the KDC, which is the Key Distribution Center, and it has a shared secret with everyone else that participates in Kerberos. And that's set of principles for which the KDC has shared keys is called the realm. So here we see a KDC has a shared secret with the client and with the file server. And our scenario is the client wants to talk to and establish a secure connection and authenticate itself to the file server. So the client begins that by talking to the KDC. It uses its long-term shared secret, usually a password, to make an authentication service request to the KDC. And the KDC replies, again verifying with that same long-term shared secret, and it issues the client a new short-term key. This is key associated with a ticket granting ticket. So we don't want to continue to expose that long-term key on the network many times, so we create a new short-term key, and the client uses that short-term key to make a request for service to the file server. KDC replies using the short-term key, and it creates a session key to be shared between the client and the file server. It gives one copy in a form that the client can read and gives another copy encrypted so that only the server can read it. The client can then form a service request to the file server, can authenticate it with that short-term key, and then it sends the server its copy of the key encrypted so that only the server can read it. Server unwraps the key, verifies the signature on the message that came from the same key, and then it can provide services to the client, optionally verified and signed and sealed, whatever, with that short-term session key. So these are the basics. And why you should care is because this stuff is everywhere. If you've ever logged on to a Windows Active Directory network, if you participated in a large-scale Unix Linux deployment on a university or any other type system where you have a large centrally administered intranet network, Kerberos is the underlying protocol for all of that. And it's not just there. Because it is so widely deployed, it's being adopted continually in new places. One of our other consultants, Andrew Becker, is going to talk about Kerberos and Hadoop later on in the conference. It's being used for web services. It's being used for InfoCard and federated services as a binding to allow intranet identities to be moved out to the web. And so it really is the sort of hidden glue that holds all of our security together in an enterprise environment and extending out to the web. We're going to start at the beginning with our advice, and look at the initial authentication and how that is set up. And I'm going to hand it over to Scott Stender to do that portion.
Well, thank you, Brad. So one of the main drivers for Kerberos v5 was that Kerberos v4 did not have cryptographic agility. All symmetric keys, all encryption that happened in the Kerberos v4 protocol used the DES encryption algorithm, which we all know, if we've been paying attention to security in the last few years, it's not sufficient to protect traffic today. So in Kerberos v5, you introduce the ability to negotiate which cryptographic primitives, encryption algorithms, hashing algorithms, and whatnot, to use for protecting different Kerberos message exchanges. Examples of what are called encryption types. I'll call them E-types during this talk for short. Examples of E-types include AES 256 and ciphertext sealing mode with an HMAC that uses SHA-1 as the hashing algorithm, and so on. So you have AES 128, RC4 HMAC, which is actually something that came from Windows. It was introduced with Windows 2000. It's not a standard, but you can find guidance on how it's implemented. And that uses a 128-bit RC4 key. You have DES CBC MD5 and RC4 HMAC, similar to RC4 HMAC 128, except for it's truncated to a 56-bit key. So how are E-types negotiated? Now, Brad just went through the whole protocol. I'm going to focus on the AS-REC exchange. Now, there is no specific standard for negotiating E-types. At best, you could call them ad hoc standards, but clients and servers are free to do more than having a standard negotiation stage. But what you'll see most often is, if you're looking at network trace, is a couple of attempts to authenticate where the negotiation happens through those attempts and error messages that are returned. So the first stage, you'll have the client send what I'll call an anonymous AS-REC. The AS-REC is authenticated using a structure called the ENC timestamp. That's just a timestamp that's AS1 encoded, a little bit more data that's encrypted using a key derived from the user's password. So at first, they do an anonymous AS-REC, which is, ENC timestamp is null, and then it has a list of E-types that the client supports. Hello, I support AES 256 and DES CBC MD5. The server responds with an AIR pre-auth required. I'm not going to just give you message, data that's encrypted with the user's key. If you're just anybody on the network, I want you to prove to me first who you are, then I'll happily send you back a little bit of information. In that message, you have a list of E-types. So it says AIR pre-auth required. By the way, of the messages, all of the E-types you sent me, I support these two, AES 256 and DES CBC. So the server responds with the union of what it supports and the set of what the client supports. The client chooses the best of them, the strongest of them. In this case, without any kind of interaction, it'll choose AES 256, and it'll use that to, use the standard derivation algorithm for going from password to key. It'll use that to encrypt the timestamp, send that up to the server, and it'll specify, hey, this is a big blob, 6BA4 ... and it's using AES 256, and then it also includes a list of E-types to be used for negotiating the TGS key, which is the next stage. The server responds with a AS-REP, which includes the key that is to be used for a TGS request that follow, the authenticator for that. So attacking E-type negotiation. Now, it's not exactly apparent if you read the specifications, the RFCs and whatnot, and it's not really apparent if you look at the network traffic. And also, if you've had experience with other similar protocols that have to negotiate cryptographic primitives, you might be surprised to find that that list of E-types, both from the server and the client, is unprotected by any kind of integrity mechanism. Right now, it's all pre-auth, and so the attacker has the ability to drop good E-types and leave bad ones behind. So what does this allow us to do? It allows the attacker, a full man-in-the-middle attacker, to drop the good E-types when the client is sending that initial anonymous AS-REC. The Kerberos server will then respond back with that AIR pre-auth required message that includes only what the client supports and that it supports as well. So if you just say, hello, I support only DES, server will look up and say, do I support DES? Yeah, great. Okay, here, let's go with the DES. You can also downgrade the authenticated AS-REC, in which case you're going to influence the next stage. Or you can intercept the server response back to the client, that AIR pre-auth required message, and you can downgrade and lie to the client about what the server supports. In both cases, the end result is the same. The ENC timestamp, that authenticator, that which is derived directly from the user's password, is going to be using a cryptographic method that's not exactly the most secure thing in the world. Now the benefits of that. So if I am able to downgrade to DES, DES is a rather older and somewhat simpler E-type than the latest and greatest. There is no keyed authenticator within the encrypted timestamp. Furthermore, the only key that's derived is the encryption key that is used to protect that encrypted timestamp. So what you have is a one-time, take this string, make it into a password, or into a key, and that key remains the same key that's always used to encrypt ASREC and timestamps from now until the user changes their password at the same time. In effect, if you get that key, you're able to have a password equivalent for Kerberos and use that for several months until they change their password once again. So the end-to-end attack scenario is, get active man in the middle on a network that uses Kerberos, downgrade that initial ASREC or the response to error pre-auth required, go down to DES. You're going to see the client emit that encrypted timestamp, and then you can hand it off to our friends who are also at this conference, Pico Computing. Here you see a card that is an FPGA cluster. Back at Blackhat Federal, they demonstrated breaking a DES key in as little as 3 days using older hardware. Presumably with more hardware and this newer hardware, we could break that down into shorter number of days or even hours. We can go ask them if we need details on that. So you break the key, now you have that long-term key, and then you can just go back to the network and use that to authenticate the user and get access to any system that they have access to via Kerberos. All right, so we all know DES is bad. How do we, is that the only thing that can go wrong? The other benefit of downgrade is that, again, the latest and greatest E-types are a bit more sophisticated in trying to protect against password grinding attacks. And by that I mean we take a big dictionary of words, we do the derivation of keys, we encrypt a timestamp and see if the encrypted timestamp can be decrypted using something that would be out of a dictionary. And we can spend a whole lot of time verifying what, trying active keys, seeing what's going on, seeing if we can guess the user's password. Franco Dwyer, several years ago, maybe 2002, 2005, I think he had an update to his paper, demonstrated that you can have efficient password grinding attacks against a strong E-type that's used widely in Windows, RC4 128 HMAC. Even if you do get rid of DES and you use only E-types that cannot be broken via exhaustive exploration of the key space, you can downgrade to something that allows for efficient password grinding attacks. So for that reason, we suggest staying with the latest and greatest because they do try to slow that computation down using PBK-DF2, which is a standard for repeatedly hashing the user's password and the output from the previous hash to make the computational difficulty of deriving a key much greater. You can specify, you can configure the number of iterations. The standard specifies that you should not be able to go below a minimum iteration count. The default is 4096, by the way. But the interesting thing about downgrading is not only can you say go back to RC4 HMAC, you can take advantage of any bad client implementation in that you can specify in that error pre-auth required optional parameters for the key derivation. You can specify the salt that is to be used, which is typically the user's full name. It's the realm and the user's name. Or you can specify the number of iteration counts. And so if you have you can use that wiggle room to perhaps make a more efficient attack. So does this affect me? We talked about DES. We all know that DES is terrible. Windows Server 2008 and Windows Vista, so the latest versions of Windows from just a few years ago, all support DES out of the box. And so the KDCs are willing to accept DES encrypted timestamps, and Windows Vista clients are willing to emit them. In addition, rather recent open source distributions of Kerberos, MIT, Heimdall, and similar ones that are configured and used similarly, Solaris for example, they also all support DES. Windows 7 emits but does not accept RC4 export grade RC4. You can have a Windows 7 client emit a 56-bit encrypted timestamp. It doesn't do you a whole lot of good because it doesn't help you get the password any faster than that R128 version. Similarly, the client or the DC will not accept that authenticator as proper authentication. And also, even if you get rid of all that, if you have the latest and greatest where everything is disabled by default or you can configure it as much, enabling DES E-types is still surprisingly required for interoperability. If you go and look around for guidance on configuring E-types in Windows Server 2008 R2, you're much more likely to find people looking for the KB to fix a patch that will allow them to, or fix their servers that allow them to use DES in certain circumstances. People require DES for older systems, and especially even as recently as right before Windows Vista was released, DES was the only common ground that MIT Kerb and Windows Kerb had for negotiating E-types. So you have it still out there for interoperability. That's why it's enabled a lot of times, and that's why it's still enableable, even though we know it's all terrible. So protecting against downgrade, in a word, disable those weak E-types. Get rid of DES, get rid of export grade. RC4, and if possible, stick to the AES ones, just because they do have that additional password complex, or the the computational complexity for deriving the key from the user's password. In addition, there's a different mechanism for deriving keys from the user's password that makes it so that even if you do break that encryption key, if through some grand advance in cryptography you are able to break that 256-bit key, you still can't forge a timestamp because it itself is a derived key. So disabling E-types. It's always configurable in MIT and similar distributions. Windows Server 2008 and R2 and Windows 7 introduced a new policy that allows you to configure E-types. And also these are just increasingly disabled by default. In the latest versions of Windows and the latest distributions of MIT, you don't have to take any, MIT Kerb 1.8, you don't have to take any additional steps. So if we get rid of those bad E-types, we still have the possibility of password grinding attacks. If somebody sets a password of 12345 or Gandalf, you're still going to be able to see that timestamp. No matter how complex it is, you're going to be able to get an efficient recovery of that password and be able to spoof that user. The response people say is use smart cards, use the public key Kerberos authentication mechanisms, and Brad will talk a little bit more about his research in that area.
All right, so smart cards are the gold standard today for enterprise authentication. If you're in a highly secured environment, you probably use a smart card to log into your Windows workstation. And under the covers, that is all still implemented in terms of Kerberos. There's an extension to Kerberos called PK-init, which allows for public key cryptography, usually X509 based PKI, and usually certificates stored on a smart card, to be used to replace this initial authentication step that Scott has just been talking about. So instead of using DES and AES encryption, we're going to use public key encryption. The client is going to send a pre-authenticator that includes a certificate and a signature made with the private key associated with that certificate. And the KDC is going to respond and send the ticket granting ticket encrypted with the client's key and signed with the KDC's key and providing the KDC's certificate. Relatively simple, only the first leg of the protocol changes. So one of the key things that you always have in Kerberos is mutual authentication. It's not just that the KDC wants to authenticate the client, it's that the client also gets to authenticate the KDC, because the KDC is then going to be the authority for every other service that the client talks to. This is relatively simple and implicit in a symmetric key situation, because you know that the only other person that has your key is your KDC. So you have, as long as you can decrypt the message, it came from the right person. In a public key situation, things get more complicated. PKI, we have chain building, we have roots of trust, we have policies, we have subject identifiers, extensions, things like that. And as we've seen in the last couple of years with HTTPS and SSL, this can be rather tricky. There's a lot of pitfalls, there's a lot of things that can go wrong. So we want to look a little more deeply into what are the validation policies for these certificates involved in public key Kerberos. So first thing that's of interest is who are the trust roots. And luckily for all of us, the usual suspects from the web are not involved. That big list of 200 CAs of varying trustworthiness or not that ships with your browser and your operating system and Java and everything else, those are not in the picture here, and we're all very glad of that. All the certificates for public key Kerberos have to be issued by a specific set of designated trusted CAs. This is usually in your Kerb5 config file for the open source clients. On Active Directory, it's stored in the directory in LDAP, in the NT-auth store, and it's also stored in the registry. Now, when you're authenticating as a client with a smart card, the way that the KDC validates that smart card certificate is it has to be issued by that authority. It has to have a subject name that matches your Kerberos principal or is mappable to a Kerberos principal. And it has to have a smart card authentication enhanced key usage flag to distinguish it from just any other soft certificate that's being used. That's relatively straightforward and implemented in the same way by almost every implementation. Where things get a little trickier is how the client authenticates the KDC. And there's some big differences in the implementations here. You still have to have that certificate for the KDC be issued by that specially designated authority. And the open source clients look for a special key purpose ID and enhanced key usage that says this is a KDC. This certificate is not anything else. It is a KDC. And you have to hope that the certificate authorities are very careful about who they issue those kinds of certificates to. Now Windows was actually, the public key Kerberos implementation was done before the specification was finalized and before this EKU is set up. So if you look at the certificates issued to Windows domain controllers, they typically don't have that EKU. So that raises the question, then how are Windows clients verifying this? And for a long time, there was no documentation, there was no indication of what that algorithm was. But a couple years ago, with Vista SP1 and Server 2008 being released, there was a new group policy that appeared called Require Strict KDC Validation. And this is obviously pretty interesting. You would hope it was always strict. But if you look at the text here, it starts to just recapitulate the verification algorithm specified in the RFC. I won't bore you with that. But the last paragraph is especially interesting, caught my eye. If you disable or do not configure this policy setting, the Kerberos client will require only that the KDC certificate contain the server authentication purpose object identifier in the EKU extensions. That's it. Server auth EKU, and it can be a KDC. So are there other certificates issued by the enterprise authority that have this EKU? One of them is the web server template. If you're in a large enterprise, how many web servers do you have and how well are they secured? If you've been following advice of people like me who say you need SSL even on your intranet, you probably have a lot of these certificates floating around. Enterprise web applications are kind of notorious for their insecurity. They might not be patched, they might be running a mix of Linux and Unix and other operating systems. You have a lot of attack surface that allows someone on your network to potentially gain access to one of these certificates. And even if you're using network access control or something like that, you're guaranteed to have at least one system on your network that has one of these certificates, your remediation server. But unfortunately, it gets worse. Because when you install Active Directory certificate services, one of the templates that's enabled by default is the computer template. And this template also has a server auth EKU. And as you can see in this screenshot, every single computer that's joined to the domain has permission to enroll for this certificate by default. So what this means is potentially any computer in the enterprise has access to a credential which might allow it to impersonate the KDC to any other client in the enterprise. And we did some testing and verified that yes, in fact, that's the case. In the default configuration, all Windows clients up to and including Windows 7 and all of the open source clients when configured to interoperate with a Windows domain controller will accept pkinit AS reply signed by a certificate issued to a web server or just using the computer template. You might wonder, well, why don't we just match the name? You know, I'm not expecting www.domain.com to be my domain controller. And it turns out you can't do this. This is our SSL, main part of our validation algorithm for SSL certificates. We can't do this for KDCs. First of all, it's not in the specification, so a lot of the certificates don't have a standard subject name field like that. And secondly, a lot of clients don't know who their DCs are when they boot up. They don't know their KDC. They have to discover it dynamically. They might have moved to a different part of the network. The administration configuration might have changed. So Windows clients are going to wake up. They're going to ask DNS SRV records. They're going to ask NetBIOS broadcasts. They're going to do a connectionless LDAP that's unauthenticated. A bunch of insecure protocols to try and get a name that they can then bootstrap Kerberos with. So there's no point in trying to match a name that you got from an insecure network protocol with the name you got in your certificate. So they don't even try. This has some interesting effects in the attack we're about to demonstrate, because if you don't do that match, you can't use DNSSEC to save you from this attack because the client isn't doing any name verification anyway. As long as you can ARP, spoof, or be an active man in the middle, you can supply whatever certificate you want, even if it doesn't match the name. And Kerberos traffic is also typically exempt from IPsec policy, so you can't rely on IPsec to protect you. So what does our practical elevation of privilege path look like? So here's our typical kinit, which is the command line used in our open source implementations on, say, a Linux system to do Kerberos and then go get a file from a file server. If we replace this and put in our imposter KDC, we can also replace our file server because we're authenticating who the file server is, and we can poison the protocol and allow for the spoofed file server location to be trusted by our victim. We can send them a Trojan or a piece of malware and take over their session. And it's actually relatively simple to accomplish. Turns out that at Windows, this is much more difficult, and the basic naive attack we just showed there fails. And this is because the victim isn't just authenticating to the KDC, the victim has to authenticate to their workstation. So they make their initial request, and then they ask for a ticket to log onto their workstation, and they send that ticket locally, inside the machine where it can't be influenced by the network attacker to complete their authentication. So when we replace our KDC with the imposter with the web server certificate, we can still capture the initial part of the protocol, but when we try and do the last ticket, we don't know this binary secret for the workstation. That's still a secret that's only shared between the workstation and the real KDC. They never use public key Kerberos, so we can't create a real ticket that lets the user log in. And we're going to get a message saying something like, the trust relationship with the domain failed. But there are ways around that problem. Domain join is one situation where you don't have a machine account yet. We're bootstrapping trust, we're creating the machine account, we're creating the machine account password at domain join time, and it's all based off of the user's credentials. So if we can intercept and man in the middle of domain join being done with a smart card, we can use that to capture and man in the middle all the traffic, discover the machine account's password, take control of it, and then when the user logs in again with permission, we can just forward that traffic, join it to the real domain, and we have a machine which we know the system password for as long as it's valid, and there's no forensic trace of us on that machine. But domain join is an unusual situation, right? You don't typically see that happening on a network if you're an attacker. Many machines are joined offline or pre-joined. We want to be able to attack regular everyday traffic. Well, let's assume we also have control of a conspiring user. If we have full control of a workstation, it's not too much of a stretch to assume we also have control of a user account with real credentials in the domain. Maybe this is a conspirator, maybe this is just someone that we've owned. There's this interesting feature of Windows Kerberos called user principal name canonicalization. This is used so that administrators can move your account around within a large directory between realms and to different parts of the organization, and you don't have to know that that's happening. You can always use the same email address to log in. And we have the RFC draft text up here for you, but the basic gist of it is that the subject on the certificate on your smart card is not definitive for what your Kerberos account and your principal is. It's only a hint. It's a pointer, and the KDC is authoritative for what your actual account is once you start getting these tickets. So if this is just a pointer, we control the KDC and we have a conspiring user. What if we make your logon point to and look at the conspiring user's account instead? So here's the attack scenario we've built here. We have our victim who's trying to log in, and we see they make their initial request and they say, hey, I'm victim and I would like to log in. I would like to get an authenticator and a TGT. And our imposter KDC says, sure, here's your TGT. By the way, your actual principal name is patient 0, which is our conspiring or pre-controlled account. Victim says, okay, you canonicalize me, that's fine. Now give me a ticket to the workstation. The imposter KDC, since they have credentials for the real user patient 0 in the domain and they can talk to the real KDC, and since most users can log into any workstation in a domain, they go ask the KDC as patient 0 for a real ticket to the workstation. They get it. They're able to unwrap it, unwrap the session key, and have the real ticket to the server issued by the real KDC. They rewrap it with the key they've controlled and given to the victim, send it along. This is a referral TGS reply because the name is different than the name that the victim thought. This will be accepted and they can use it to log in. So now we have a situation where the victim has logged in with their smart card, but they came in as somebody else. So is this really an elevation of privilege? We assumed at the beginning we had control of patient 0, and now we have a login session as patient 0. So we haven't elevated privilege yet, but we're in a very good position to, because a user started at a trusted, healthy workstation, has no malware on it whatsoever. They put their smart card in, they typed in their PIN, and they got logged on as someone else. They have no reason to expect that that's going to happen. That's completely unusual behavior. And furthermore, that login interactive session now we control. We have control of that patient 0 account. We have control of the KDC. We can change their login environment. We can run commands on that desktop. We can push group policy. So we'll push a Trojan that pops up the screen as soon as they log in that says, installing updates, please do not turn off your computer. And we hang around for 10 minutes, and then we pop the screen that says, insert your smart card to unlock your workstation and type your PIN. User types in their PIN, it unlocks, says, please wait, we're rebooting. They reboot, they log in again, everything's fine. But what really happened was they forgot to hit Control-Alt-Delete. Pretty common. They're used to putting in their smart card and typing their PIN. They think it's a trusted system. But really that Trojan program just captured their PIN. In user mode, it's able to unlock the smart card module, make a TGS request to the real server, and now it has a credential it can renew for up to 7 days and access any service in the enterprise as that user. Smart card TGTs also contain an additional field, a supplemental credential buffer, that has your NTOWF in it so that you can do NTLM authentication. And for smart card only users, that doesn't change pretty much forever. So now I can also have a very long-term credential that lets me authenticate to any service in the network that accepts NTLM. So we basically started with one computer and one user, and we're able to, by network attacks, silently elevate and take over any other user's credentials that uses smart cards to log in. This is a complex and difficult elevation path, but it also leaves almost no forensic traces. The protocols can't be firewalled. They're all the same normal protocols you need to log onto your domain. And all of the things that are different about the attack versus the real protocol are hidden inside the encrypted portions of the protocol that a network sniffer can't see. And as I said before, IPsec and DNSSec won't save you. So what would we do about this? Well, we have that strict KDC validation policy I mentioned earlier. You can turn that on for Vista SP1 and above. It is not available for Windows XP, but frankly, if you're worried about this level of attack and you're running a 7-year-old operating system, you probably have bigger problems and you need to get working on that first. Before you can turn on this policy, you need to enroll all your domain controllers for an updated certificate. The template is available in Windows Server 2008 and above. It's the Kerberos authentication template. The reason these policies aren't default is because older KDCs would not have this, and if you just turn on this policy, nothing would work. So enroll your KDCs first and then turn on the policy. For domain join, it's very hard to push policy and secure this before you join to the domain, since the domain is usually your mechanism for policy. So either set this policy on your system images, domain join offline, use a password for joining to the domain, and audit who is able to and who has actually joined machines to the domain. On the typical open source clients, they do supply the CKU with their standard server certificate tools. So if you're in a purely Unix or purely Linux environment, this probably doesn't apply. But if you are in an environment where you're interoperating with Windows and you have this require EKU flag turned off, you can turn it back on after you've updated your certificates on your domain controllers, and then you'll be safe. And really, there's a lot going on here. I've just kind of glossed over the top of it. So I would encourage you to go visit ISEC Partners' website. There's a 20-page paper we're going to release later today describing the attack in a lot more detail and a bunch more hardening recommendations. And Microsoft yesterday also published a 20-page paper giving step-by-step instructions for network administrators to enable all the flags and secure against this attack with screenshots and the whole deal. I would put the link up, but it's about 150 characters long and has a GUID in the middle, so it won't do you any good anyway. So just go to isecpartners.com and we'll have a pointer to that for you later today. So we've bemoaned and attacked initial authentication, but that's only sort of just incidental to the process of Kerberos. What we're really trying to do is get service from an application. And there are a whole other set of pitfalls that come with that, and I'm going to hand that over now to Rachel Engel to discuss those.
Thank you, Brad. So at this point, we have typed in our password, and we have gone to the KDC, and we've got a ticket to talk to the service that we want to talk to. Ultimately, though, your reason for using Kerberos is to check email or connect to LDAP, and that piece of the protocol is happens with the AP rec and the AP rep. This is a request and response. So what happens there is you send a request, and when you send that request, at this point the client has a copy of a session key. They send the request, and the request contains a copy of the session key that can only be read by the service. After this request and response happens, both the client and the service have a copy of the session key. A lot of the time, Kerberos is called a single sign-on protocol, but what it's really good at is establishing a session key between two authenticated principals on your network. So we've established this session key between the client and the service. But have we authenticated yet? Well, not really. The service has this key, but does it know who the client is? No. It has to have some information from the client that it can use to determine whether or not the client is the person it intended to talk to. And that comes in a piece of data called the authenticator. So the server decrypts its session key it takes that and it uses that to decrypt the authenticator, and then it looks at the information in the authenticator. But think about this. All the client has done to authenticate is send a request. So what's to stop an attacker sitting in the network from taking a copy of the request? Nothing, initially, from what we've talked about so far. You can take that, Mallory, if no protections are in place, can take that request, send it on to the service, and authenticate as the user. If the developer isn't careful, this works. This requires developer care to prevent, and so we'll go into that. How do we prevent this? Well, the authenticator, it contains a couple of pieces of information, and if you look, some of those pieces of information are designed to at least do some prevention of replay. One of them is a timestamp. This is used to determine the freshness of the ticket, so if Mallory gets a copy of that request and then goes away, has lunch, comes back later, tries to use the request, at that point it's not going to work because it's not going to fit within the freshness window. But the timestamp is just big enough to detect clock skew, but if Mallory is actively editing the traffic in the network, Mallory is going to be able to beat the freshness window, so this is not going to stop Mallory. There's a replay cache. The service takes a copy of the request, stores it, and then looks and sees if subsequent requests are the same request, and if it's the same request that's already received, then it's replay. However, if Mallory is sitting there on the network actively editing the traffic as it goes across, Mallory can win and have the first request, so the local cache isn't going to stop it. There's also a checksum. This is more interesting. So the checksum can take a checksum over application data. That also goes in the authenticator. But if you think about it, a single checksum at the time of authentication isn't good enough to provide integrity for a full bidirectional protocol. So what do people do with it in practice? People do lots of things with it in practice. Sometimes they set it to nothing, which does really no good. RCP sets it to a checksum of the contents of the command line arguments. SSH sets it to a magic number. It is not a random number. It is not particularly entropic. It is a magic number, but it is effective. If I take a request that was sent to authenticate another service like Telnet, and I try to use it in the context of SSH, SSH is going to check the checksum and see that Telnet did not set the checksum to anything, and it's looking for its magic number, and it will reject it. So effectively, it's an informal service binding, which means that you can only do replays again that have been of requests that have been intended to be sent to that service. So if none of these pieces of data prevents a replay, what do we do? You'll perish in flames. Well, you will not perish in flames. It is not quite that bad. Earlier, I said that what Kerberos is really good at is establishing a session key between two authenticated principals on a network, and it is very good at that. When the request and response have been sent, both the client and the service have a session key. This session key can be used to do integrity protection of the protocol. So I'm developing a protocol, and what I need to do when I authenticate with Kerberos is take that session key and use it to provide integrity. If Mallory at this point goes and takes the request and tries to send it to the service, perhaps it will not be detected as a replay, but when Mallory tries to start sending traffic, it will be noticed as being inauthentic because it does not have the integrity protection that's appropriate. So this actually works, and this is effective. This is why the attack is possible, because preventing it requires developer care. So what we can do is developers should be careful to integrate the session key into the integrity protection for the protocol. Administrators should look at their Kerberos deployment and check the services to make sure that the integrity protection is integrated with authentication. Also, since Mallory was getting the copy of the request by intercepting traffic on the network, also having some encryption and integrity between the two endpoints via Stunnel or IPsec would prevent Mallory from getting the request in the first place. Although if Mallory breaks the security guarantees of either of those protocols, then the same advice still applies. The session key established authentication needs to be integrated into the rest of the protocol. And for what to do on Windows, I'm going to hand it over to Scott.
Hi, as Rachel noted, in the Unix world, you typically will be using Kerberos quite directly. And there are a couple of other APIs you can use that will use Kerberos under the covers. But in the Windows world, you're almost certainly abstracted from the details of Kerberos via an interface called the Security Service Provider Interface. Now, you can use SSPI directly to roll your own use of the negotiated security service providers, one of which is Kerberos, others are NTLM, and so on. You can use that directly if you want to roll your own cryptographic binding, and that's something that people might do with just a raw TCP socket. But the other 99% of Windows developers are almost certainly going to be relying on the integrated Windows authentication that you get for free when you use major protocols that are exposed in Win32. So in order to make that cryptographic binding that Rachel talked about, making it so that the application protocol has at least integrity protection, maybe integrity and privacy, then you have to use the application programming interfaces for those protocols correctly. So let's go through those protocols one by one. LDAP. LDAP is used in Windows to communicate with the KDC primarily, but it can be used for many other things. There are two major APIs that Win32 exposes. One is I'll just call it the LDAP API. I'm not sure if it has a better or more specific name, but what's great about that API is you can specify the specific SSP you want to use. You can say that you want to use Kerberos with it, and then there are also flags for requiring integrity or integrity and privacy. There is another API that's available called ADSI, which is widely used, and it's a little bit more Active Directory friendly. However, it doesn't allow you to specify the SSP. You can specify whether you require signing or signing and sealing, meaning integrity or integrity and privacy. You can specify that. However, you can't specify that you want Kerberos and all the goodness that Kerberos provides. If you do want to use ADSI and you do want to make sure you use Kerberos, best way to do that is to have the administrator turn off NTLM on your clients and servers, which is an option that's available with Win 7 and Windows Server 2008 R2. Now, RPC is purely over in the developers world. RPC allows for very granular control over your SSP and what they call authentication level that you get with your packets. You can specify, I don't care whether it's authenticated or not. You can specify, I would like to see that AP rep, but I don't, or the AS rep and or AP rec and AP rep. But I don't care if you use that session key later on. That's called connect level authentication. But the ones you want to look for are packet integrity and packet privacy. Those names come from the constants you use when you specify it. But on the client side, you can say that this binding handle is going to use packet integrity, packet privacy, and it's just going to plumb that session key from the depths of SSPI and use that to protect the packets. On the server side, you use what's called a callback function. When you register your RPC service, you can specify a function that gets called for every RPC call. And in that function, best place to check for, or that function is best place where you check for packet integrity or packet privacy. And you have all this RPC context that you can query. You can find out if it's using Kerberos, packet privacy, packet integrity. For those that want IPC on Windows, it is both local and remote. I recommend RPC, even though it's a little bit more complicated to get going. You have such granular control that you can almost certainly meet your security requirements. DCOM is a little bit higher level than RPC. It actually uses RPC under the covers, but it provides a slightly different and easier programming interface. On the client side, you can specify that the context, what they call the proxy, requires packet integrity and packet privacy. And on the server side, rather than using a callback function, you actually have to either specify what level you require when you register your COM object, or you can say, I'm going to let the administrator handle this using what's called an application identifier, which means that the COM object will look in the registry, find out what the administrator says it should use, and then make sure it has that level of protection provided. Administrators can then go and configure that level using the component services MMC snap-in. One interesting thing, though, is that because of legacy interop, the default level, that if a COM object doesn't specify it, or if it specifically says, I would like to see the default, please, the default level is connect, meaning that the replay attacks that Rachel talked about generally are very possible if your object does not override that. We administrators, including all of us who are using our machines here, go and change that to packet integrity or better. I recommend you do the same. So then, SMB and name pipes, which are just built on top of the SMB protocol. I'm sorry, developers, you have no control over the SSP or the integrity level provided on the content that goes over there. Your file shares, your name pipe-based IPC, you can't specify anything from the developer's perspective to make sure that you're getting what you need. However, the administrator can. There is a security policy, it's a local policy, it's a group policy that allows you to require signing on all SMB traffic. That'll hit both of those protocols. And it's something that you can either specify, don't require anything, negotiate signing, or require signing. We all love require signing. Question up front.
I think that implies a fair bit of overhead, which is why it's not on my default.
Okay. The response was it does require a fair bit of overhead. And so if you do have performance problems, then you might have to leave that off. But certainly if it's an untrusted network and we want to make sure that those replay attacks are not possible, you want to turn that on. So if you have a completely trustworthy network and low performance, you might want to leave it off like anything else. But if it's a non-trustworthy network, which is the kind of network we tend to use authentication protocols on, you probably want to turn that sucker on. Is that a fair response? Okay. HTTPS. Now this is a new one with Windows 7 and Windows Server 2008 R2. You can get integrated Windows authentication using HTTP, but there's no packet privacy setting that you can specify for an HTTP connection. This is because it's a very widely interoperable type of protocol. So what they've introduced in the latest versions of Windows is what's called a channel binding token. It's under the feature called extended protection, and you can go and look up more guidance on that. But briefly, what happens is when you're using integrated Windows authentication over a SSL connection that's using the HTTP protocol, the client will emit a token that indicates to the server, hey, I'm trying to use SSL and I'm trying to talk to this server. Would you please make sure when you receive this packet that nobody messed with that you didn't see something that people were intending to use for HTTP or a different server. The server also has to be configured to check for that token and do that specific step I just suggested. Now, unfortunately, this feature is disabled by default. You have to go and change a couple registry keys on the client side in order to emit that token, and then you also have to configure your IIS server to check for that token. So mostly administrator side, devs, it pretty much comes for free. However, if you are doing something a little bit off the beaten path, you should look up some documentation for what you can do, specifically with .NET clients. So we've gone through authenticating properly, making sure we don't have bad crypto, making sure that our PK init deployment is nice and happy. And then we went through, okay, now we just rewrite all the services in the world and configure our machines properly to actually use that session key that Kerberos negotiates. Now, thankfully, are we finally done? Now, one of the benefits of Kerberos is true mutual authentication. That if I want to talk to Brad, between all that stuff we just talked about, especially that AP-REC and AP-REP, I can make sure that I have a session key shared with Brad. Now, what happens if I'm using a big, huge, large-scale, self-organizing system? How do I determine that Brad is the person I want to talk to? I can do a couple of things, but maybe we'll just start with a few things maybe you shouldn't do. So one idea is ask the attacker what their SPN is. If I type in, I would like to connect to 192.168.0.2, how do I find out what their SPN is? To go to the Kerberos DC or the KDC to find out what the SPN that I should be using to get a key to that one is? Well, I could just ask the attacker, please tell me, who are you really? Another idea, maybe, Brad?
Well, instead of rolling your own way to ask the attacker, you could use a standard API like RPC management inquire server principal name and ask the man in the middle over documented, standardized interfaces what identity they would like you to use.
It's very helpful. Rachel?
Oh, you could check the DNS SRV record. DNS is totally secure.
Yeah, that's another good idea. Just ask out into the ether, hello, who is my LDAP server, please? Another one is you can pull the attacker's SPN out of a service definition defined by the attacker. If we're using the promise of service-oriented architecture and just have a self-organizing beast of systems and we have all these WSDL documents going around, when we pull down that WSDL document, we're probably pulling it from an attacker and we're looking at the SPN within that document. Next one, Brad.
You could also just pretend that this doesn't happen and not set an SPN at all or set one that's incorrect. And if you're very lucky, your service will default to something somewhat sensible, but you're not sure. More likely, you're going to not use Kerberos at all. You think you will, but you'll get NTLM or you'll get a null session, and you won't have any indication that that's happened.
So unfortunately, the list of things not to do is much easier to create than the list of things to do. It's a surprisingly widespread problem because if I'm just talking to Brad, that's pretty easy to figure out who I'm talking to and to type it into my, my little login prompt or whatever else. But if I have 100,000 machines, all of which are going to be service-oriented perhaps, or maybe configured for ease of deployment so that they go and resolve who they're supposed to be talking to and authenticating with, then there is no standard recommendation for what to do. You could write down on every service or every endpoint the 10 principals you're supposed to be configured to talk to, but that's error prone and it doesn't scale. The best argument I can give is you have to make sure you have secure service resolution, that if you are going to be doing runtime mapping of what your SPN is, that you do that through some bootstrapped authentication to maybe a service resolution server, and then you use that to find out, okay, I know who you are. You are myhappyserver.isecpartners.com. Please tell me, who should I be talking to for LDAP? So you want to do that over a secure channel, and a lot of times when I've had to run into those things, when we've had to run into those things before, it's a deployment and application specific sort of thing. So if you have questions, please do ask us directly. So thank you all for coming. This was a very high and fast presentation. There's a lot more content. If you have questions about your specific use of Kerberos, please do feel free to email us. And as we continue to do research in this area, we'll be posting more updates. And so check us out at isecpartners.com. Thank you for coming.